All right, great. So the second talk is on SwitchLog, a DSL for network switches. From the presenter is Vaibhav from Princeton. Take it away, Vaibhav.
Yeah. Hi, I'm Vaibhav, and today I'll be presenting our paper on SwitchLog, which is a logic programming language for network switches. And this is joint work with Devon, Loehr, John Sonchack, and David Walker. So before I start, hopefully that stays on. But so before I start describing our language, I'm going to give a little bit of background about networks and network switches and what makes them so hard to program. So until not very recently, if you wanted to build a new network or a new data center, you had access to a very small set of routers and switches that were sold by a very small set of companies like Cisco and Juniper. And so you'd end up buying devices that looked something like this. And what's more is that this equipment was closed, proprietary, and vertically integrated with features already baked into the hardware. So as you can imagine, this made network management and configuration extremely difficult and messy. And what's more is creating new features was close to impossible. So for example, if you wanted to build a custom routing protocol for your network or data center, you had to go and request the vendor to actually change the hardware of their switch to accommodate you. And so naturally, this cycle took a lot of time, and this led to a lot of loss in productivity and time, and at times even money. And it also made innovation really hard, right? Because if every time you want to try something new, you have to request a hardware change to some big company, that's not feasible. And this wasn't great. And as data centers and networks became larger and larger and more complex, people realized they could do a lot better in terms of optimizing performance if they were able to implement custom routing solutions as well as custom applications for their network switches. But to do this, they needed programmable hardware, which they could customize on their own. And this led to the development of the programmable switch. Now, and with the development of programmable switches, a whole new world opened up for programmers. Now they could implement all kinds of new, exciting, and interesting applications for their switches. For instance, people implemented new and optimized custom routing protocols. They implemented interesting monitoring and telemetry applications, which allowed for proper network intervention at the time. And they also implemented interesting security applications, right? For instance, applications that could detect and prevent denial of service attacks on these networks. However, programming these switches isn't easy because they're extremely specialized hardware. They're designed to deal with hundreds of millions of packets per second. So they're very constrained and not general purpose. So most general purpose programming techniques don't work on these switches. And programming them isn't easy. And to see why, I think it helps to understand the architecture of these switches a little bit. So this is what a typical network switch consists of. So first you have a programmable parser. So when a packet comes in, it's parsed. And then it's passed through this pipeline, which is programmable. And this pipeline can consist of tens of stages, depending on the kind of switch you use. And each stage in the pipeline has a small amount of memory and can perform a small amount of computation, such as looking up a match action table or some basic arithmetic, and also read write to the memory. But the catch is that once an instruction in one part of the pipeline has been executed, you can't go back to that same instruction again, which means you effectively can't have any kind of iteration or loop on these switches, right? Which is in part what makes them so efficient, but it's what also makes them so hard to program, right? No loops. However, sometimes you need these loops, they're unavoidable. So the way around this is a method that's known as packet recirculation. So once a packet has been processed by the pipeline and the deparser is done with it, you can take that packet and pass it back in again to the programmable parser and and process that same packet again. So in effect, you've created a loop. And this is at times necessary and used in practice. But every time you recirculate a packet, you're lowering the bandwidth of the network, right? So you want to avoid this as much as possible and minimize packet recirculation. And So the standard programming language used today to program these network switches is called P4. P4 is really low level and provides almost zero high level abstractions. You literally have to specify what you want to do at each stage of the pipeline, when to look up a match action table. And so programming in P4 is extremely tedious. Even a simple application can take thousands of lines of code. So, as a result, subsequent work has tried to provide higher level abstractions. For instance, Lucid provides an imperative language like abstraction that builds on P4. There's another work, Sonata, which provides other declarative language abstractions. All of these build on P4. And we continue to explore that design space with SwitchLog, where we look at logic programming abstractions that build on top of P4. And the nice thing about these logic programming abstractions is that while P4 applications can take thousands of lines of code, in even like 3 or 4 lines of switch log code, you can express interesting and non-trivial switch programs. So in exploring this logic programming abstraction, we were inspired heavily by NDLog, or network data log. So network data log is another logic programming language for networks. So it builds upon traditional data log by providing control over where data log facts are stored. So in a distributed setting, you can say which switch or which router you want your data log fact to be stored at. And this is done via a location specifier, which is the @ symbol. So for instance, this is what a typical NDLog rule looks like. And you can see how every predicate, the first term, has an @ before it, which tells you the location of the fact. And if you look at the second rule, you have on the left-hand side next at self, and on the right-hand side you have next at n, which tells you that these are two different predicates at different locations. And this difference in location is what leads to communication between switches or routers. And this is quite remarkable because you're able to express communication without any send or receive primitives, right? But the problem is NDLog is designed for software switches and not hardware switches. And it won't work given our hardware constraints. And to see why, I think it's best to go with an example. So let's say we were trying to create a data log like language for a switch that did routing. So our setup is as follows. You have 3 switches, A, B, and C, each of which are connected with each other with some cost. And this is expressed by some base predicate. Let's call that link. So link AB4 says that A is connected to B with cost 4. And link AC1 says A is connected to C with cost 1, and so on. And our goal is to compute a table like as follows, which is to say that the best path from A to B is via C with some cost 2 plus 1, which is 3, or that the best path from A to C is via C with cost 1. So how might we go about writing this rule in standard data log or in NDLog? So we might have these rules, which we saw earlier. So the first rule says that there's a path from self to n with via some next hop n with cost c, if there's a link from self to n with cost c. So using this first rule, we can derive that there's a path from A to B via B with cost 4, or there's a path from A to C via C with cost 1, right? Now let's look at the second rule. It says that there's a path from self to D via n with cost C, if there's a link from self to n with cost c1, and next, and there's a path from n to d via some n prime, right? So for instance, using the fact that c can reach b with cost 2 and the link between a to c, we can then derive that a can reach b with cost 3, right? And similarly on switch b, using the fact that c can reach a with cost 1, and rule 2, we can derive that B can reach A with some cost 3. So now we have a bunch of paths with the next hop. We need to find the minimum, right? So we'd use the standard data log minimum aggregation operator. So we'd say, right, given all these paths with these next hops, find the minimum cost. And as you can imagine, to execute this minimum operator, we'd have to iterate through all the derived next tables on switch A, for instance. So we'd see next ABB4, and we derive min cost from A to B is 4. And similarly, the min cost from A to C is 1. Then as we continue the iteration, we'd see that the min cost from A to B is actually 3, right? And so this iteration, you can imagine on a network switch, would correspond to some kind of packet recirculation. And the number of derived tuples could be arbitrarily many. So that's arbitrarily many packet recirculations, right? And this gets worse, right? Because now we need to join this cost to the actual neighbor which has this cost, for which you might have the following rule, which is that the best path from self to D is via N if the minimum cost from self to D is with some cost C, and the path from self to D via N also takes that cost C, right? And since we don't know what N is, given a min cost tuple, we have to again iterate over all the derived next tuples to actually compute our best table. So for min cost AB3, you'd have to go through all the next tuples and you would find that, okay, the cost 3 matches the tuple where the path is via C. So you get best ABC3. And similarly, you get best ACC1. So we just saw that there were two main sources of iteration in this example, min and join. And these iterations required a lot of packet recirculation, right? So if we were to directly take standard data log or NDLog and implement it on a network switch, this would be infeasible and too expensive. Your network would basically have no bandwidth. So our goal now is to come up with a restricted declarative language such that its rules can be evaluated efficiently on the switch. And at the same time, there's always this trade-off between when you're restricting something. We want our language to be able to express interesting applications that network switch or data plane programmers might care about. So the first thing we need to do is a way to avoid iterating over facts. And to do this, we introduce key value semantics, which is that every SwitchLog table has keys and values rather than it just being a single set. So this is what your SwitchLog table declaration looks like. The first term, like before, is the location where the tuple is stored. So it's a location specifier, similar to NDLog. The next few terms are annotated with the keyword key, which specifies that these are keys, and the rest of the declaration is just values, which can be looked up given these keys. And we also have type declarations with each term, and you might see that there's an interesting type lock there, which is a special type that represents switch locations. So this is different from a location specifier in the sense that a location specifier tells you where the fact is stored, so at which switch, and lock just tells you that this field contains a switch ID, not that, and it doesn't tell you anything about where it's stored. These switch IDs are actually just typically subsets of integers, but it's a small finite range of values. And the motivation for this will be apparent soon enough. So the natural question to ask when you have any key value semantics is, what do you do if you have the same set of keys but different values, right? And so to solve this, we introduce merge operators, which I'm going to explain by way of example. So the merge operator we're going to look at is min. So the first rule is a SwitchLog rule which says ABC XY V1 V2 if P XY V1 and Q XY V2. X and Y, which is the terms in red, are keys, and V1 and V2 are values. And you have merge min. So what merge min will do is, given two instances of ABC with the same keys, so you have ABC1254 and ABC1229, the SwitchLog minimum will pick the tuple with the minimum value of V2. So in our case, this is ABC1254, and that will be derived. And this helps us maintain the invariant that for a given set of keys, you have just one derived fact. Now, on the second rule we have is a standard data log rule with the minimum aggregate operator. So if you have ABC XYV1 min V2, if R XYV1 V2, and notice this has no keys and values. So to see how our minimum operator is different from the data log one, you could go through, I'll just illustrate how the data log operator would work. Let's say you had three tuples, R1254, R1256, and R1229. The data log operator will find the minimum V2 for a given XYV1. And as a result, you'd be able to derive both ABC1254 and ABC1229. So this is slightly different from our merge operator, and this difference becomes important. And in addition to min, we have other operators such as count. Count increments the argument a, which is typically a value, by some amount n each time a fact with a given set of keys is rederived. And this is pretty similar to the count aggregate in data log. And the absence of a merge operator is treated as recent in which case we retain the most recent instance of a fact to be derived. And this is useful to simulate things like changing network conditions. For instance, if a link goes down, you might want to, you only care about the most recent fact that you derived. Now, this key value semantics alone isn't enough to restrict our language. We need other syntactic restrictions, in particular to deal with joins. And to see what I mean, I'm going to again go by way of example. So consider these three SwitchLog table declarations. So you have P1, which has one key and one location specifier and one value. P2 also has a location specifier, a key, and one value. And you have P3, which has a location specifier, two keys, and two values. Now consider the following rule. So P1 self YZ if P2 self YZ and P3 self OQZW, right? So you can see that the keys in P3 differ from the keys in P2, right? And let's say we get an instance of P2. So we have P2 at 153, that's at our switch, and we want to evaluate this rule. So we need to check if P3 self OQZW is true. But notice that we don't know the keys of P3. We don't know O and Q. So without iteration, how do you actually go about checking the truth value of this predicate? So, well, the answer is there really isn't a good way. And now consider this example. You have P1 self YZ, P2 self YZ as before, and now P3 is self OYZW. And you receive the same predicate, P2 at 153 on our switch. Now we know Y and we know self. The only thing we don't know is O. But notice that O is of type lock, and lock is a set of, and lock refers to, sorry, no, P2. It should be P2 because, I mean, you want to derive P1 given P2, right? So, sorry. So the only term we don't know is O, which is of type lock. And lock, we said, is the set of switch IDs, which is typically a small finite range of values which we can iterate over, or that is allowed. So to evaluate this rule, we would iterate through all possible values of O, or all possible locations, or which is the number of switches in the network, and then check the value of P3, and we'd be able to evaluate this rule. And this leads us to our first restriction, which is that all predicates on the right-hand side must have the same set of keys, except that one predicate may have an additional key, which must be a location. And we said location here because the location type is a small set of finite values. In principle, this could be any user specified type, so long as the programmer can guarantee that this will be a small set of finite values. And the second restriction we have, again, we'll go by way of example. Consider the following rule. P1 at self YZ if P2 at AYZ and P2 at BYZ, right? So let's say you receive P2 at 253 on our switch. Now this P2 at A is stored at a switch that's different from self, right? So in principle, we could store it, but we don't want to because memory on our switch is limited. So it would be quite bad if we went around storing facts that were coming from other switches. So now I don't store P2 at 253, but I still need P2 at BYZ. So let's say I send out a query for P2 to switch B, which, right? And now let's say I get the result of this query. So I have received P2 at 353 from switch B on my switch. But I'm kind of stuck again because I never stored P2 at AYZ. So I don't really have a way of evaluating this rule unless I query again and I keep on going on forever. So kind of stuck there. So this leads to the general restriction that no more than two unique location specifiers may appear in a rule. So in the first rule, you can see you have self A and self. So there's two. And in the second rule, you have self A and B. So as a result, so this is the second restriction we have. The third restriction is, this is a hardware restriction, is if the same relation appears multiple times, it must have a different location specifier. So for instance, here we have P1 at self and P1 at self appear twice. And this is an issue because switch hardware doesn't really let you look up the same table twice without recirculation. So if we had this, you'd have to perform recirculation every time you wanted to evaluate this rule, which is kind of what we're trying to avoid. So in the interest of time, I'm going to skip this demonstration of how routing with our SwitchLog examples work and talk a little bit about how SwitchLog is compiled. So SwitchLog is compiled to Lucid, which is a high-level language, which is eventually compiled down to P4. And the key abstraction that Lucid provides is events and event handlers. So an event, for instance, might be an incoming SwitchLog tuple that we just saw, and an event handler would be a function that then executes upon this incoming SwitchLog upon this incoming event or incoming SwitchLog tuple. So for every SwitchLog table, we associate an event and associate event handler, and then we also define a rule, which is an event handler for actually evaluating the rule, which is kind of like a function that's called to actually evaluate the rule. And finally, we use lucid arrays to actually store the SwitchLog tables themselves. So overall, this is what the execution looks like. So you have an incoming SwitchLog tuple that comes to your switch. So you call the event handler for the tuple and you actually store the tuple. Then one of three things can happen. So there's some rule that's dependent on this tuple, right? So you see if this tuple has all the keys needed to evaluate the rule. And if it does, then you can just call the function to evaluate the dependent rule and you're done. The second thing that might happen is that to evaluate the dependent rule on this tuple, you need another tuple that's stored on another switch, in which case you can just query that other switch for that missing tuple and then take the result of that query and evaluate again on the original switch. And the third thing that could happen is that if any rule needs an extra key, we loop through all possible locations because we know that the missing key must be of type lock. So you loop through these locations and you call the event handler again. So SwitchLog, like we saw, is very good at creating tables like routing tables or other telemetry systems. But these switches often want to perform actions based on the contents of these tables. So sometimes you can just create these tables and have a controller switch look at them and read them. But other times you want your own switch to be able to use these tables themselves. And to overcome this, we integrate SwitchLog as a sub-language in Lucid, which means you can create switch tables using SwitchLog and then refer to them in Lucid programs. For instance, on the top left, we have the full code for a routing program in SwitchLog. And then we have a Lucid function, which actually looks up this next table that we created with its neighbor field, and then forwards a packet based on the table we created. And this is really powerful because SwitchLog and Lucid have a nice synergy where Lucid is very good at expressing this kind of forwarding logic and looking up tables. And SwitchLog is good at creating these tables, which can be a little difficult in Lucid. So earlier we had said that we want our language to be restricted but also expressive enough. And to measure this, we implemented some representative data plane applications across a variety of different types. So for instance, Mac learner and router are two common examples that involve communication between switches. A stateful firewall is an important security application, and NetFlow cache, distributed heavy hitters, and flow size query are important telemetry and monitoring operations. So as you can see, the SwitchLog program takes only a handful of lines of code, whereas the corresponding Lucid and P4 program takes way more lines of code. And in terms of resource usage, we don't even use, so we compile this to an Intel Tofino switch, which has 12 stages. So the SwitchLog programs are efficient enough in that they don't even use all the stages. And per stage, we use approximately 20% of the available resources. And as for recirculation, which is the key metric, as you can see, the 4 telemetry operations don't even require any recirculation, where the Mac learner and router do require recirculation, and this is proportional to changes in network topology. So in some senses, this is unavoidable. Even a handwritten P4 program might employ recirculation in these cases. So in conclusion, SwitchLog is a logic language for network switches, and we're able to combine advances in data plane programming and logic programming to create a language that has a natural and concise syntax, can express a lot of applications naturally. So still an open question as to what kind of limitations these restrictions have on the kinds of tables that we can generate. we haven't had much experience, but in our experience, all the applications which involve generating tables that we've tried to build, we've been able to successfully implement. But I suspect more experience will tell us that there's probably classes of programs we can't implement. Thank you.
Questions, anyone?
Many thanks. Do you verify properties of the programs you write in SwitchLog?
We don't, but one of the motivations for doing it is that verification of SwitchLog programs should be easier than P4 or Lucid programs, just because of how simple the program is and because there's a lot more work that's been done on verifying programs, logic programs like NDLog, for instance. So that is kind of a future target for us.
I see. Thanks.
More questions? There's still a couple of minutes left.
Hi. You mentioned that SwitchLog is based on NDLog, so we can refer to tuples that are on other switches. What's an example where we, sorry if I missed this, but what's an example where we need a tuple on another switch? And how does one switch ask another switch for that?
Right. So the example where you would need one, so I'm just going to go back, is the routing example I showed right at the beginning. So, oops. So you can see how in the second rule you have a next at n. It's kind of tiny here. You have a next at n and you have a next at self, right? So the n refers to another switch. So routing is one example where you might want to. And as for how do you ask, so so for us in SwitchLog, Lucid provides high-level primitives for querying other switches, which compiles down to some P4 primitive for sending a query to another switch. And sometimes this can amount to just literally sending a packet which says, hey, can you respond to this? So yeah, that's kind of it.
I have a question. Do you take into consideration bandwidth, the network bandwidth, when you do your SwitchLog, or is it already a part of NDLog?
So the whole point of these restrictions is to minimize network recirculation, which is what is typically the main source of bandwidth reduction. And you're right, communication between programs would also reduce bandwidth. So that depends on the kind of program you write. For instance, the telemetry applications we showed would have no effect on bandwidth. But if you had a program which fundamentally needed this kind of querying, then it would. But SwitchLog programs don't require any more queries as compared to an equivalent P4 program that expresses the same logic. It's just a different way of expressing the communication.
There are no more questions. So let's thank the speaker, Vaibhav. We'll move on to the next talk.